Okay, we'll start with the welding processes. Welding processes as used in shipbuilding industry primarily. We'll look into that. So there, as you can see, generally all the welding techniques involved, there are fusion welding processes, right? Here I have listed some of them which are more relevant as far as the shipbuilding industry is concerned. Amongst this fusion welding means where fusion takes place. By virtue of fusion, you do the joining of two components. So SMAW, that is shielded metal arc welding. Then you have GMAW, gas metal arc welding. GTAW, gas tungsten arc welding. We'll take them up little more in detail subsequently. I am just now highlighting what are the methods. SAW, submerged arc welding. Then you have something called electro slag welding, electro gas welding. So these are as we can see 6 such methods which are based on fusion welding process. Then we have another welding process which can be referred to as solid state welding. By solid state we mean that there is no fusion involved, there is no melting involved. That is how the name solid state. So under that a welding technique which is referred to as friction stir welding, that is also slowly gaining so called popularity and acceptance in the shipbuilding industry. In this, we do not go for melting of the plates to be welded. So that is how the name solid state welding. We will look into that later, little more in detail. So today we will look into this shielded metal arc welding little more in detail. So as you can see, this shielded metal arc welding, why it is called shielded metal arc welding? Essentially it is the arc is shielded from the environment. As you can see in this schematic diagram, these dotted lines, they are actually shielding the arc as well as the primarily the arc from the environment, from the atmosphere, such that contamination, oxygen or nitrogen contamination does not take place, right. So essentially this is a fusion welding process, right. It the required heat is produced from an electric arc. All these fusion welding processes which I have just now mentioned, of them these first 4, the heat is generated from electric arc. So they are some form of electric arc welding. There is some form of electric arc welding, right. Whereas this is, it is actually electrical resistance, the heat generated from the electrical resistance. Resistance of molten slag. That is how the name electro slag welding, because all these are fusion welding process. So there you need to have some heat generated which will melt the metal as well as the electrode, right. So in the first 4, the heat is generated from electric arc. In this electro slag welding, it is generated from the molten slag, right. Again, electro gas is from electric arc, right. It is also from electric arc. Here essentially a gas shielding is there. We will see how it is different from the gas metal arc welding later. So again, going back to this shielded metal arc welding, as you can see that here the required heat is produced from the electric arc. Between the tip of the flux between the tip of a flux coated electrode and the surface of a base metal, the electric arc we have between that, obviously. So, here we can see that the electrode as well as the filler metal is the, that is one and the same. So, this is schematically shown, you must have done it in your first year workshop practice. So, here what you see is that this is our electrode. Here we have the covering, the coating over the electrode. The central part is the core wire which carries the current and acts as the filler metal too, right. Here you have the so called the welding arc, right, electric arc, where schematically we have tried to show that the metal transfer is taking place. These black spots are as if what happens, the metal gets melted and it gets transferred through the arc column, right, through the arc column. So, here your molten metal from the electrode is getting transferred to the base metal, part of the base metal is getting melted also, right. Thereby, you have the weld metal deposit over which you have a solidified slag. That slag is nothing but the burnt flux, the coating what it has over the electrode. That burnt flux is termed as slag, and the slag under that heat remains in a molten state. So, which floats over the weld metal and thereby provides a shielding to the molten metal, right. Whereas, in that heat the flux will burn and generate some gases. Those gases protects the arc column, the plasma column. Plasma column also needs to be protected from atmospheric contamination. Why? Because through the plasma column you have the metal droplets getting transferred. Electrode tip is also there at that high temperature. So, if it is not shielded from the atmospheric environment, the metal getting transferred as well as the electrode tip will get oxidized, right. So, what you see in the shielded metal arc welding is it's essentially a manual welding process. Also at times it is referred to as MMAW, manual metal arc welding, right. Also it is referred to like that. So, here what we have is the one of the important constituent is the welding electrode, right. Depending on the different types of electrode, the welding quality, end usage of the welding process also changes, varies. So, we will take a look at the what are the kinds of welding electrodes, the broad classification. So, electrodes are nothing but it has a metal core with a flux cover, right. Electrodes have certain standard length electrodes are available. So, they have the required metal core. That metal composition will depend on your usage. That means, of course, if you are going to weld certain particular steel material or some metal object you are going to weld. So, you will have to choose the suitable electrode for that purpose. Choosing suitable electrode means you will have to look into the weld metal composition or the parent metal composition which is to be welded, such that matches with the welding electrode, right. And then other aspects which concerns the flux, right. So, that we will see. So, here what you see is that the metal core acts as the electrode as well as the filler metal, as we have seen, because for electric arc welding you need to establish the arc. So, to establish the arc you need an electrode. So, here the electrode is a consumable electrode. It generates the arc, generates the heat, and in that heat the electrode itself gets melted and gets deposited. Thereby, we do the welding. So, primary function of the flux cover, why the flux cover is there? The metal core we can understand. The flux is, it provides shielding to the welding pool, to the weld pool. Weld pool means when you strike an arc under that action of the heat, the part of the base metal just below the arc melts and forms like a molten pool, of metal. That molten pool is referred to as the weld pool, right. So, the function of flux cover is, one of the function is shielding the weld pool, and during metal transfer from the electrode tip to the weld pool from atmosphere. That means that molten pool has to be shielded as well as the arc column has to be shielded, because metal transfer is taking place, as I have already said. So, that shielding is provided by that arc column shielding is provided with gases created. From where it is created? By the coating decomposes under the arc heat, the flux coating that burns and decomposes under the arc heat and produce the necessary shielding environment. That is what is referred to as welding fume. When you do a metal manual arc or shielded metal arc welding, you will find a lot of fumes getting generated. They are purposely generated, means the flux composition is such that those fumes are generated, because those fumes are needed to give a shielding, to give a coverage to the arc column as well as the arc electrode tip. Whereas the molten metal is given a shielding by the molten slag, right. So, that is what has been said here. The gas is not enough for proper shielding, means the fumes, welding fumes which are getting generated, or the gas which is getting generated, that does not give the entire shielding. So, what happens? The flux coating burns and produces a protective slag. The flux, after getting burnt, we refer it to as slag, right. That keeps the molten metal, weld metal shielded from atmospheric contamination, because atmospheric contamination is, primary contamination is oxygen, it will get oxidized, and also nitrogen. There is a nitrogen contamination also takes place. So, to protect it from that, this protective slag or the molten slag acts as a protective coating. This molten slag has lesser density, thereby it floats off the molten metal, because when I am welding it, your metal is getting melted, flux is getting burnt, forming slag, and that is also in molten state. So, both are mixed, but the molten slag being lighter, it will float up the molten metal. So, that is also important, because it should have sufficient fluidity, the molten slag, such that it can float up, because the molten metal, the weld pool in the molten state is not remaining for a very long time, because you are moving the electric arc, you are doing the welding, and doing welding means one of the motion is you are taking away the heat source, electrode is moving. So, as you are taking away the heat source means what? The molten pool is also moving, or in other words, the molten pool is getting solidified. So, the slag should be able to float up before it gets solidified. They are in a mixed condition, because under the action of the arc, there will be quite a substantial turbulence in the molten metal pool. In that turbulent environment, your molten metal as well as the molten slag, they are in a mixed condition. So, it should have, the molten slag should have such property, such viscosity and density, that it can float up very fast and gives the protection. And because if it cannot float up, then it remains entrapped within the molten metal, solidified metal, which is then a defect in the welded joint, right. So, the layer of slag thus forms not only prevents the deposited metal from atmospheric contamination, it also does another work, as you can see, also slows down the cooling rate, because what is happening, if you go back to that here in this schematic figure, this is the solidified metal. Say this is my solidified layer, over that it is the solidified slag. So, when I am doing the welding, as I am progressing, I will find there is a layer of slag remaining over the weld bead. What is that weld bead? That is nothing but the solidified metal. That means there where the metal deposition has taken place. So, it does that additional work, that it slows down the cooling rate, because as the solidified metal or the weld bead is covered with a layer, and obviously this slag which is formed, that will have that is a bad conductor of heat, and it is covered with that. So, that leads to reduction of the cooling rate, and we know if the cooling rate is slower, then it produces a more ductile material, because steel, as you know, if the cooling rate is very fast, that is what is referred to as quenching. You heat up a metal and dip it in water, it becomes hard, it becomes brittle, but you heat it up and allow it to cool very slowly, it is annealing, right. So, somewhat that effect of annealing takes place. So, thereby the slag functions not only in terms of protecting it from oxidation, from atmospheric contamination, also it helps in a positive sense that it makes the weld deposit ductile, because always is preferable to have ductile property than a hard in such fabrications, right.
Sir, in the solidified electrode, where is the slag? It is on the covering or with the metal it is?
Not solidified electrode, you mean to say the electrode. Electrode is something like this, a rod over which the above the top coating is the flux, then we call it flux. Like you can see here, this electrode covering what we have written, this shaded part, right, electrode covering, here it is a section taken, right. So, this covering is the flux, that is what is, that is a solid flux, a solid coating over the metal wire. Suppose you have a metal wire inside 3 millimeter dia wire, which is actually the electrode, over which you have a coating, another thick coating of few millimeter diameter, right, few millimeter thickness. So, that is what is the flux coating. We will see what the flux is made up of, right. So, now when the arc is struck in that heat, the core electrode, this is the core wire, that is the core electrode, right. That core wire melts, at the same time the coating, which is the flux, it burns. Coating is not melting, that is burning, because it is in the atmospheric environment with oxygen, it is burning. And after burning, like the inside core wire is melting and forming a molten deposit, flux is burning and forming a slag. Flux, burnt flux is referred to as slag, right. Yeah, the slag is forming, and that slag is in molten state, and also because of the burning, part of the flux gets decomposed and forms fumes, gases, right.
Molten slag.
Yeah, not actually, molten slag is not forming any gas. This flux is forming molten slag plus gas. Like you burn a piece of coal, right? What you get? You get some gases as well as some ash, some residue. So, here the residue is the slag and some part is the gas, right. So, the gas what we are getting here, that is to our benefit. When the piece of coal is burned, the gas, it goes in the atmosphere, it does not benefit us in any way, but here it benefits us, because that gas, it protects this arc column, because through the arc column, when you have the electrode, it is not touching the metal, there is a gap. Through this gap, the molten metal is getting transferred, the electrode tip is melting and is getting transferred. So, while getting transferred, it will get oxidized, because there it is not protected by the slag. Slag is only on the above the molten pool. So, this is exposed, as well as the tip is exposed. So, the fumes coming out, right, that is protecting it, right. That is how it is said that the this gas gives the shielding for the arc. And then here we are talking about that that is not enough. So, flux slag also provides the necessary shielding. Anyway, so what you see, that the chemical composition of the flux, we have seen that there is some flux coating on the electrode, right. Now, that chemical composition of the flux coating, that has a great influence on the performance of the welding, on the end quality of the weld deposit, and also on the process, on the performance. Like it influences the arc stability. Arc stability means what? That means the arc is nothing but it's a plasma column. The gas in between that gap between the metal plate or the job plate which is being welded and the electrode tip, there whatever gas is there, to start with it's only air, atmospheric air, right. Now, when unless until you have the circuit closed, current will not flow. So, if I just hold the electrode like this, nothing will happen, isn't it? You may have observed what you do, you just touch it and then lift it up. By touching and lifting up, what essentially I am doing? By touching, I am completing the circuit. It's a high amperage power source. So, momentarily that touching will generate enormous heat here, right. And by lifting it, what happens? That heat itself will, as well as the arc created because of just breaking the circuit by lifting it, you may have observed when you switch off a switch, there is a spark kind of a thing, right. That means when the electrical connectivity gets disconnected, there is a arc, a kind of a arc jumps between the two poles, right. So, when I am touching it and lifting it, two things are happening. The momentary touching, huge current is flowing because there is a momentary short circuit in the entire welding circuit. That current will heat up the electrode as well as the base metal at that location. Second thing, the moment I am lifting it up, that there will be an arc between the electrode and the plate. So, both the action of the arc and the heat will ionize the air column there. To start with, it will ionize that. Those things will happen in a millisecond, nanosecond time. It will ionize the air column, and once the air column is ionized, it is no more non-conducting, it becomes a conducting column. So, the circuit is completed, right, and current flows. Current flows means what? Flow of electrons takes place or bombardment of electrons takes place. In the process, that heat is generated in that plasma column, right. That heat then keeps on melting the metal as well as the electrode. Now, that will keep on melting provided the arc is stable. If the arc gets extinguished, then there is no heat. Again, you will have to strike the thing, create the arc. So, that is what is the arc stability. That means a stable arc will give you a stable heat. If now and then the arc is getting extinguished or arc is getting deflected, arc power is reducing, increasing, fluctuating, then what happens? Your heat generated is fluctuating, because at the end we are interested in the amount of heat generated. We are not truly interested what is happening to the arc or what. Interested in heat generated. Why? Because that heat will determine how much metal is getting melted. Heat will determine how much the best metal is getting melted. What is the rate of deposition? All those things will depend on the heat, right. That is number one. So, to get that heat uniformly all through, I need a stable arc. To get a stable arc, I need a suitable composition of the flux coating. Why? Because initial starting, I said the plasma column is formed by the ionization of the atmospheric air, but subsequently that atmospheric air is replaced by those gases which are being generated by burning the flux, right. So, the flux composition is becoming important. That means what gas is getting released, their ionization potential becomes important, right, and that leads to the question of arc stability. So, we see that the chemical composition of the flux coating, it influences arc stability. Next thing, it influences the depth of penetration. Depth of penetration means you are striking the arc, that heat, how much it is penetrating in the metal plate. How much it is penetrating in the metal plate means till what extent it is melting the plate, how much depth. That of course also will depend on the thermal conductivity of the plate material, but also will depend on the arc characteristics. arc characteristics means what? Whether that arc has a certain kind of kinetic energy to force the jet, the arc jet into the metal plate, whether it creates a turbulence whereby the conduction process is enhanced, kind of metal movement. You assume a molten material, a zone where you have some molten material and the molecules are moving in this direction. That means the metal is coming and going down, again going through the side up and going down, or in other words like this. Suppose the fusion zone is this, and what I was saying is the movement is something of this order, of this nature. Then what happens? It has a kind of a penetrating force, right? Conduction of heat will be more, so your depth of penetration increases. Whereas if the movement of the molten particles are like this, just the opposite, as if it is going from bottom and taking an outward motion, then I have the heat is conducted more on the sides, the wall fusion is more, it is becoming wider, whereas in this it is becoming deeper, narrower and deeper. So, all those again will depend also on the chemical composition of the flux, because this will depend on the what kind of forces are generated, right. It will also affect the metal deposition rate. Obviously, the heat, how much heat is getting generated, is not only from the point of view of how much power is being spent, but also the ionization potential of the gas, that also determines how much heat will be generated. Like in a helium environment, some amount of heat, argon environment, some another amount of heat will be generated. So, that will then decide on the, will have effect on the metal deposition rate, because metal deposition rate is nothing but the melting rate of the electrode which is getting deposited. Then positional welding capability. Positional welding capability means, you know, welding. I mean, if you see welding situations, the best welding situation is like this. That means downhand welding. Metal transfer is taking place in the direction of gravity. This is called downhand welding, right? Say this is my welding electrode, this is what is downhand welding, right. There can be a situation, say this is a vertical wall, right, and you are welding in this direction, say the vertical wall, and you are welding on the vertical wall. So, this is a horizontal welding. It is in horizontal welding. You may have just the same thing, another vertical wall, and we are going up, vertically up. So, that is a vertical welding. And the worst is overhead, right, and you are doing the welding, this is overhead. That means taking the electrode and doing the welding overhead. So, this is the worst. Metal transfer is taking place against the force of gravity. In the next worst is vertical welding. Metal transfer is taking place against the force of gravity. So, there is a tendency of metal dripping. little better than that when I am doing a horizontal welding, also metal transfer against gravity, but uniformly all along, right. Best is downhand, right. So, these are called positional welding. Taken together, it is referred to as positional welding. So, what it says that the capability, positional welding capability also will depend on the flux coating composition. These we are talking for manual metal arc welding, for shielded metal arc welding. So, that means a particular type of electrode may be suitable for downhand welding, may not be suitable for overhead welding. If you have to do a positional welding, means where generally by positional welding it means any welding position other than downhand. That means where your metal transfer will be acting somewhat against the gravitational force, right. So, these are the aspects: arc stability, depth of penetration, metal deposition and positional welding capability. They are influenced by the chemical composition. So, the first flux composition, what it serves, what is the purpose? Like it induces easier arc starting. Induces easier arc starting means what? It is easy with the suitable flux composition, you will have a favorable gases generated which gets ionized more easily, such that the electric arc is initiated very easily. If you recall your workshop practice days, you may recall that many a time you had difficulty to initiate the arc, isn't it? Just change the electrode, take a suitable electrode, arc is initiated very easily. But with the same hand, you take some other electrode, you may have difficulty in initiating the arc. Well, that may have other advantages, that coating. This coating may have other disadvantages, but one of the thing is that a suitable composition may help you in easier arc starting. This is nothing but depends on the ionization potential of the gases. Stabilize the arc, that is also is there, so that you get a fairly stable arc. Then improve weld bead appearance and penetration. Weld bead appearance means nothing but when you do a welding, this is what is the appearance. Bead appearance, that means the bead profile, it has to be smooth. If it is very rough, this is not a good bead, this is a better bead. Have a smooth surface. Why it is important to have a smooth surface? Because you should remember that at the end you will have to give a coating of paint to protect it from corrosion. When a ship hull, or the offshore platform will be working in a marine environment, you will have to give a protection. If the surface is rough, then the protection will not be proper. The paint fill, life of the paint fill will be less. So, it is preferable, it is desirable to have a smooth bead surface. That is what is referred to as bead appearance. And penetration, well, such that proper fusion takes place along the thickness. Reduce spatter. What is spatter? Spatter is essentially when you are doing welding, a molten pool has formed, isn't it? Under the action of the arc, a molten metal pool has formed. So, and the metal is getting transferred. Little in an enlarged view, suppose schematically it is like this. Here you have the molten metal, molten pool, you have the arc, and the metal droplets are getting transferred. So, as it drops here, there can be a case of sputtering, right, or spattering. It is not exactly sputter, that is a different phenomena. It's just, it's something like when on a molten in a cup you have water and you drop something, some water gets splashed. Something similar, the molten metal is getting splashed out. So, that is what is referred to as spatter. Obviously, this spatter is not a good aspect to happen. Why? Because the moment it is getting splashed means that metal is getting wasted. It is getting out of the molten pool and getting deposited on the side, which has to be eventually removed. You cannot leave them as there, because they will form otherwise small beads. They have to be removed. So, this spattering is not a good thing. So, a suitable composition will reduce the spatter. Well, so that is what is the what you see the what it does and what purpose it serves about the flux composition. So, we see what are the basic different types of flux covering. So, the different types of electrodes, right, they are either referred to as cellulosic electrode or retail or basic electrode. Right. These are the broadly under 3 heads the electrode are classified based on their flux coating, composition of the flux coating. So, cellulosic electrode, what is that? The flux is rich in cellulose, right. The flux composition is rich in cellulose. It burns to produce hydrogen and carbon monoxide, which provides shielding to the arc. So, you can see the welding fume which is generated, and the person who is welding, is not very healthy for him, because there is a carbon monoxide evolution is there. So, that is why whenever there is a manual welding is done, you have a proper means of extracting the fumes, such that the welder does not get much exposed to the fume, right, such that there is a suction system, because as the welding arc is moving, the gas is generated there, giving the necessary shielding, and then it is getting dispersed in the environment, and in that environment the welder is sitting, and that environment is not very healthy, it is a carbon monoxide. So, it has to be extracted. That is another issue, of course. Anyway, so we find cellulosic electrode because of its organic compound, primarily based on carbon. So, it produces carbon monoxide as well as the hydrocarbons, they decompose and forms hydrogen, right, which provides a shielding to the arc, right, it provides shielding to the arc. So, these are suitable with DC power and electrode positive polarity. So, cellulosic electrode if you are using, they are suitable for using with DC power. DC power means when you are doing the welding, electric power source is needed. So, it can be either DC or can be AC. So, that is what it is suitable with DC and with a configuration of electrode positive polarity, because as we change the polarity, the performance changes. If I am using DC, keep the electrode negative, the performance will be different. We will see those aspects later. So, presence of these gases in the arc with high ionization potential, this hydrogen and carbon monoxide, they have a high ionization potential. It results in high arc voltage. So, you can see how it is affecting the heat generation. The hydrogen and carbon monoxide, they have a higher ionization potential, which results in high arc voltage and therefore a high arc energy. Arc energy is increasing. That results in a deeply penetrating arc, means a cellulosic electrode where you need to have a higher penetration depending on the plate material to be welded, depending on the situation, because you know how much will be the weld fusion. The penetration means this depth of fusion, right. To increase that, primary driving force is the current. You increase the current, more heat is generated, because heat is directly proportional to the square of the current. More heat is generated, so more penetration will be achieved. But these are other aspects which also helps in improving penetration. So, that means to achieve a finer control on the deposition pattern, on the fusion pattern, right, you will have to take a cumulative effect of all the welding variables. So, one of the welding variable is what is the flux, what is the shielding medium, what kind of shielding medium, what properties it has. So, that also affects the deposition rate, the deposition pattern, the fusion pattern, right. So, that is what we see here, that in cellulosic electrode it results in deeply penetrating arc and a rapid burn off rate. Rapid burn off rate means what? It's essentially, there is a term used, burn off. It's not burning off, it's melting the electrode, right. Calling for higher welding speeds means what? Higher heat is generated because of high ionization potential, higher energy we am getting, arc energy, that means higher heat. If higher heat, then it gives me a deeply penetrating arc as well as higher melting of the electrode, thereby I can increase the welding speed, right. And also other aspect is what? As much of the coating is of carbon origin, so little slag is left on the weld deposit, that means not much of slag is left there. So, that has other effects. One of the good effect of the little slag left means the less chances of slag inclusion. What I was telling, that the slag should get floated up, it should float up such that it does not get trapped inside. So, less possibility of such thing happening, that is number one. Again, at the same time, a thinner layer of slag coating, so that annealing effect will be little less, it will be somewhat little less. So, on one side you have advantage, other side you may have a little disadvantage. It is not a pure disadvantage, because you may not need that level of annealing, whatever its shielding it is giving from heat dissipation, good enough. But the idea is to know that there is little slag is left on the weld deposit. Why? Basically, it gets burnt out and it forms carbon monoxide. Well, with strong plasma jet, it produces a forceful arc, fine. So, makes the electrode suitable for all position welding. So, thereby we see, since it results in a deeply penetrating arc, a forceful arc, deeply penetrating arc, forceful arc means that it will fuse, the fusion power will be more along the thickness direction, right. Having a strong plasma jet means throwing of the molten metal also will happen with a force. So, it can overcome the gravitational pull and the metal can be deposited even in overhead condition. The molten droplet should be able to travel against the gravitational force, right. So, that is happening because of this strong plasma jet. So, that is how it makes it suitable for all position welding. So, if I have to do a overhead welding, then you have to look for a cellulosic electrode, one of the solution. The basic features of this cellulosic electrode, just to summarize: deep penetration in all position, right, suitable for vertical down welding. Vertical down welding means when you are coming down vertically, from the top coming down vertically, because going up is easier. In positional welding, when you weld from bottom and going up, it is easier. Why? Because continuously the solidified metal is giving you support. You understand? You have the suppose a vertical up welding you are doing, means you have two plates, they are standing vertically and you are doing the welding up. So, what is happening? That gradually I am progressing like this. So, this solidified metal itself is providing me support. The metal is getting transferred, it is getting a support, the solidified metal below. But when I am coming down from top, that is a different thing. The molten metal will tend to fall off because there is no support below. So, here it says that it is also suitable for vertical down welding, because there can be situation where I cannot go from bottom up, I have to come from top to bottom, right. So, it is not only has a good penetrating power in all position welding, also suitable for vertical down welding. Reasonably good mechanical properties, that means, well, the weld property what we get there, I mean these are all qualitative, reasonably good we are saying. High level, well, here another aspect, as you can see that the gases it was generating is hydrogen and carbon monoxide. Now, hydrogen is one aspect which causes a phenomena called hydrogen embrittlement. Hydrogen embrittlement. Hydrogen embrittlement means as if hydrogen is rendering the material brittle. Suppose a steel you are welding, and what actually happens, the hydrogen embrittlement, the effect of that is after the welding is over, then you find some portion it is cracked. Now, why cracked? As if the metal became brittle, so it cracked under the stresses, thermal stresses. So, it has been found that what happens is during welding, this hydrogen in the atomic state, it gets diffused in the microstructure. I won't say it is getting trapped in the molten metal. No, that's a different issue. It's going in the microstructure in the atomic state, and then as the temperature is coming down, those atomic hydrogens, they are combining to form the hydrogen molecules. It's not two molecule combining, it's to form helium. It's hydrogen atoms combining to form hydrogen molecule. And now, what happens? Two atoms and one molecule, there is a difference of volume. So, that exerts a tremendous force. So, schematically, it could be seen something like this. Suppose these are your crystals, or you see under high magnification the microstructure, these are the grains. Now, these locations, if we think, they are the kind of voids wherein your hydrogen has gone in, right. So, they join together to form hydrogen molecules. So, thereby they exert a tremendous force in all direction. Right, and that force, if the microstructure, the metal cannot sustain, the crack will form. A crack will form, right. That means a crack initiation will take place, and then under the action of external forces or forces due to thermal stresses, because you have welded, it got heated up and getting cooled down. So, kind of thermal stresses are forming. So, under the action of that crack further propagates and a failure takes place. That means a long crack forms. So, this phenomena is referred to as hydrogen embrittlement. Right? So, the culprit is hydrogen. So, to avoid hydrogen embrittlement, you will have to avoid hydrogen in the welding source, in the welding place, in the weld metal. But unfortunately, here the flux cover is such that it evolves hydrogen. So, this is one of the bad aspect of cellulosic electrode. That means high level of hydrogen generated risk, high level of hydrogen is generated, that the risk of cracking in the heat affected zone increases. Well, heat affected zone means that is the weaker zone. So, possibility of cracking developing there, it increases. So, that is one of the bad aspect of cellulosic electrode. Then we come to the rutile electrode. What are the rutile electrode? This contains high proportion of titanium dioxide. The titanium dioxide is another name is rutile. That is how the name rutile electrode. So, the flux contains a high level of titanium dioxide. this titanium oxide promotes, well, this promotes easy ignition, smooth arc operation and low spatter. All that we saw in cellulosic electrode. Also similar things we are finding, that titanium dioxide, it is actually titanium dioxide anyway, does not matter, titanium oxide or titanium dioxide, that promotes easy arc ignition by virtue of titanium oxide being there in that flux coating. Arc ignition is easier. It leads to smooth arc operation. Smooth arc operation means stable arc, and also low spatter. So, classified as general purpose electrode with good welding properties. So, these retail electrodes are the so called general purpose electrodes, means in a wider range of field, wider range of requirement purpose, it can be used. Because of the retail and the ionizers in the coating, some ionizers are added in the coating. These electrodes can be used with either polarity and in all position. There we talked about in cellulosic electrode positive polarity and preferably with DC power source, right. There was a limitation, DC power source with electrode positive. Here we find that it can be used with either polarity and in all positions, and the moment it becomes in either polarity means I can even use AC source. That means for general purpose welding you can use that, but definitely for shipbuilding or there where you want a superior quality of weld property, etc., naturally you will have to well, I mean you have to look for whether this gives you the required mechanical properties or not, right. So, these electrodes are specially suitable for fillet welding in horizontal and vertical positions, right. So, the basic features of this, to summarize, they are it has a moderate weld metal mechanical properties. As you can see, these are more generalized kind of electrode which can be used over a general wider range, right, in all positions everywhere, but it gives a moderate kind of mechanical properties. Mechanical properties achieved are not of high order. Good bit shape produces because of viscous slag. Bit shape is, bit profile is good because you have the slag viscous, means it forms a viscous covering over the molten metal, thereby you get a good bit profile. Positional welding possible with fluid slag. Slag is sufficiently fluid enough, all position welding is possible. Slag removal is also easy, right. This is also important aspect. After the welding, the slag has to be removed. It should be able to remove easily. If you cannot remove easily, there will be a possibility of small pieces of slag remaining on the weld bead. And if you have to do multi-run welding, that remains entrapped, because that will not float up, a solidified slag. So, slag removal is also another aspect which should be looked into while designing the coating. Then basic electrodes. This contains high proportion of calcium carbonate and calcium fluoride. Right. These are referred to as low hydrogen electrodes. We have just now talked about hydrogen embrittlement. So, these are low hydrogen electrodes, means here you can achieve a environment where hydrogen evolution is minimal. So, makes the slag more fluid than that in case of rutile coating. It is more fluidic slag. Slag is of first freezing type, suitable for vertical and overhead position. Why this? Slag gets frozen and that provides support to the molten metal also, right. So, it is more suitable for vertical and overhead position. The coating composition is produced with a very low moisture content. Why? Because they are low hydrogen electrodes. So, we will have to control the moisture content also, otherwise it may generate the hydrogen. In cellulosic, the composition is such the hydrogen evolution was there, but here question of hydrogen is not there. It comes from atmospheric moisture if the coating has absorbed. So, we will have to see the hydrogen content of the deposited metal is usually less than other type of electrodes. Weld deposits have low hydrogen content, makes them suitable for welding low alloy steels susceptible to hydrogen heat affected zone cracking. So, these basic electrodes are suitable for welding of low alloy steels, means higher tensile strength steels. If you have to weld, you have to use basic electrodes for high tensile steels, because low alloy steels are generally high tensile steels. It has a high resistance to hot cracking. Hot cracking means because of the thermal stress, the crack takes place still when the weld metal is in hot condition. Suitable for welding of thicker steels and steels with higher carbon content. The moment it is higher carbon content, the possibility of harder phase, martensite phase formation increases. We have talked about this. So, weld metal has excellent mechanical property. In the retail, we have seen moderate. In cellulosic, we have said good. Here we say excellent mechanical property, particularly impact property. So, in shipbuilding, that says that in shipbuilding applications, it is preferable to use wherever manual welding, use a basic electrode, right. So, these electrodes are used for high quality applications, which calls for low hydrogen content. To prevent electrode coating from moisture absorption, they are to be properly stored and dried. Like for example, when you are welding HSLA steel, HSLA is high strength low alloy steels, right. Their additional baking immediately before welding is needed. Immediately before welding, you bake it. So, what is done is they are directly used from a dryer, a portable. The welder carries a portable dryer, it kind of a flux, as if, right, which is electrically heated. You keep the electrodes inside. It's something like if you have seen Ramayana and all that. Rama used to carry the arrow, that container of the arrow, something similar, exactly similar. That kind of a thing. Instead of arrow, you keep the electrodes, okay, and there that is electrically connected, such that you continuously keep them at an elevated temperature, and just take out the hot electrode and start welding, such that you minimize the possibility of moisture absorption, right.
What is baking?
Baking is that. Baking is heating of a certain item at a certain temperature level for a certain time, right. That is baking. At a certain time, you hold the thing at a certain temperature level, so as to drive out the moisture, right. So, this the basic features are the weld deposit with good mechanical properties, low hydrogen content in the weld deposit, relatively fluid slag. But you see, everything is good, but this is bad. Poor bead profile. Generally, the bead profile becomes somewhat more rough. Slag removal is difficult. These are the two negative aspects. Okay. All right. So, that is all about the shielded metal arc welding. Next, we will look into gas metal arc welding. Okay. Oh. Well, there is something about metal powder electrode that also maybe we will talk it about in the next class. Okay.